Section 18.6, the quantization of angular momentum. The angular momentum of this 3D rotation has three components: Lx, Ly, Lz. Lx is ypz minus cpy, Ly is zpx minus xpz, Lz is xpy minus ypx. The corresponding operators are here. You just need to replace pz with negative I h bar times delta over delta z. You replace this py with negative I h bar times delta over delta y. That's it. This expression is the classical physics expression of this factor L. And this is quantum mechanics. This L is a three-dimensional operator. And this x, Ly, Lz are the operators in the x, y, z directions. We can prove this Lx and Ly do not commute. That means we cannot determine Lx and Ly simultaneously and exactly. So how do we prove this? We just need to evaluate the commutator of Lx and Ly and show that this commutator is non-zero. So the commutator of Lx, Ly is Lx times Ly minus Ly times Lx. We just need to apply this to an arbitrary function f. And this is the expression. Now we plug in the expression for Lx, Ly, Ly, Lx. And we expand everything. We get 5 terms here and 5 terms here. And this is I h bar squared. This is negative I h bar squared. So if you pay attention, these two terms in red cancel. These two terms in blue cancel. These two terms in purple cancel. The two green terms cancel. In the end, we have just this minus this. The result is I h bar times Lz operator. So this is Lz operator. So anyway, the commutator of Lx and Ly is non-zero. We cannot determine this two exactly simultaneously. Similarly, Ly-Lz commutator is I h bar times Lx. The Lz-Lx commutator is I h bar Ly. So we just can't determine this two simultaneously. We cannot determine this two simultaneously and exactly. This is the result of non-zero commutators. Now let's look at this L. The eigenvalue of the eigenfunctions of this operator, this is L squared operator, is this. So this is the eigenvalue. Well, this helps us to determine the magnitude of L. This is actually the angular momentum squared. So the magnitude of the three-dimensional angular momentum is the square root of L times L plus 1. And then times h bar. So basically the square root of this. The square root of this is the magnitude of the three-dimensional angular momentum vector. We can also find eigenvalues for the Lz operator. It's just m sub L times h bar. This m sub L is from negative L to positive L. There are a total of 2L plus 1 possible values here. M sub L times h bar is the z component of the three-dimensional angular momentum operator, and we can prove this L squared commutes with Lz. So that means we can determine L squared and Lz exactly and simultaneously. Now let me give you one example here. When L is 2, M sub L can be negative 2, minus 1, 0, 1, and 2. So the magnitude of the three-dimensional angular momentum vector is the square root of 6 times h bar. The reason is L times L plus 1 is 6. What about the z component? The z component is negative 2, negative 1, 0, 1, and 2 times h bar. So there are 5 possible values for the z component. This picture will give you a better idea about the magnitude of the vector and its z component. So you are looking at 5 vectors here in red. Every vector has a length of the square root of 6 times h bar. So this is square root of 6 times h bar. This is also square root of 6 times h bar. Same here, same here, same here. 5 different vectors. And their z components are also different. The z component of this one is 2h bar. The z component of this one is h bar, 0, negative h bar, negative 2h bar. So again, we have 5 different vectors because they have 5 different directions. Although they do have the same length. In this case, L is 2, so the length is the square root of 6 times h bar. Okay? Now let's look at the picture again. It's telling you the vectors of the three-dimensional angular momentum of a particle rotating on a sphere. This particle may rotate about the x, y, and z axis at the same time. Well, except in this case. In this case, the particle does not rotate about the z-axis. The particle only rotates about the x and the y-axis. All right? So, but in general, the particle rotates about the x, y, and z axis at the same time. However, it's impossible to determine Lx and Ly simultaneously, or Ly Lz, or Lz Lx. It is possible to determine the magnitude of the three-dimensional angular momentum and z component as illustrated in this picture.